My name is Martin, and the clickbait title of my talk today is how to get the 30,000 foot view, the 1 foot view, and everything in between without breaking the bank. So to give a little bit of context on myself and the project that we'll be basing this presentation on today, for the past 4 years, I've been working on M3. M3 is an open source metrics platform that was open sourced out of Uber. And at a very high level, there's 3 main components. There's an aggregation tier, M3DB, a time series database, and a query engine as well. Now, it can ingest metrics in all the standard open source metric formats like Prometheus, StatsD, and Carbon. And you can also query it using all the standard open source query languages such as PromQL and Graphite. And if you really like using SQL, you can do that as well through Presto. So we've given quite a few talks on M3 over the past year. In fact, Pratik was here just a year ago at Monitorama on this very stage, talking about why we decided to build our own time series database and the performance, scalability, reliability, and efficiency gains that we got by doing so. So if you weren't here last year, please go check out that video, a link to the video and the slides are right there. I wanted to call out one of the slides that he presented last year in particular, and this slide was comparing the efficiency of our legacy system, which was Cassandra, to our own new system, M3DB. And you can tell that even though both were horizontally scalable, the efficiency of the systems really impacted the slope, and M3DB was far more efficient, which was great. In case you can't see, the y-axis here is cost, and the x-axis here is the number of series that we were storing. Now, we fast forward this a little bit, about a year, and we see that very quickly, even though we had a more efficient system, very quickly we caught up to the same amount of hardware we were using before. Now, for the same amount of hardware, we were storing more metrics because it was a far more efficient system. So we're getting 7 times the amount of storage, or the amount of metrics we could store over the previous system. But this grew really quickly, and it was quite alarming to us that people were pumping billions and billions of metrics into the system. So we decided to sort of dig in and find out what was behind this. So stepping through an example use case of M3, let's pretend we're a backend developer. We own a backend service. This service exposes a couple of endpoints, and we serve requests from both mobile clients, iOS and Android. So if I wanted to sort of instrument my service and figure out what the latency was, I could do so with a single line of code. This is written in Go using one of our metric clients. And you can see here, if I wanted the latency, I can create a histogram called latency, and I can add a few tags to it so I can slice and dice my data. The tags that I'm adding to it here in this example is the status code, so the HTTP status code of the result, the name of the endpoint, so I can differentiate my endpoints, the type of client that the request is coming from, so iOS or Android, and also the version and the host that the service is running on, so I can figure out which, potentially a source of the problem. So I have this deployed, and now I can get a pretty good view of the latency of my endpoints. I can graph it on a per endpoint basis in Grafana, and that works fairly well. And now because I have all those tags onto it, I can dig in. So I can dig into one particular endpoint in particular, such as the request endpoint, and I can break that down by the version that's running. So I can see how the new version of my code is comparing to the old version, because I've added that as a tag. And we can see a discrepancy here where the new version has slightly higher latencies. So I can further dig into this now and break it further down by the other tags I have on it, so I can see what the difference is between the requests coming in from iOS clients and Android clients. And again, we see a discrepancy here, and the yellow line representing the iOS clients is slightly higher. And finally, we can dig in even one level deeper with the final tag that we got associated with it, and we can even break down based on the service running on which particular host to see if there's a discrepancy there to potentially narrow down the problem to a single piece of hardware. So this is pretty good. I get a top-level view of my endpoints in terms of latency, and I can drill down all the way based on the tags that I've added to it. Now, as I scale out my service, I add more endpoints to it, and I deploy it to more hosts. And what I notice with my monitoring is that at the top-level view, now I'm getting more endpoints because I've added more endpoints, the top-level view where I'm viewing the latencies of all of my endpoints, this graph slowly starts to degrade. It gets slower and slower to load over time, and eventually you just get back an error completely. So hopefully this is something you've experienced before. And the error message says something like, you're trying to request too much data now, and we can't serve it to you. Now, the reason why this is happening is something we talked about a little bit at this conference, which is high cardinality, but not in the way that you might expect. So if we look at the cardinality of each of these tags, there's nothing unreasonable here. It's not like we've added any additional tags, and it's not like we're emitting like a UUID or a timestamp in these tags. These are all very reasonable cardinalities for each of the tag values, The highest one is the status code, and there's 17 of them, and there's just 17 different HTTP status codes we can give back. So we're not abusing the system in a bad way, but of course, every unique combination of a tag name and a tag value produces a unique time series. Hence, when you multiply all of them out, you get about 230,000, right? There's also 10 for the histogram, just because we're creating 10 buckets for this particular histogram. Now, the problem with 230,000 series is that it's extremely expensive and resource intensive to try to load that in a single query. So even though your graph may only be pulling back 2 single time series back to Grafana, and it looks like just a few pixels, to generate that, we have to actually sum up every one of those single 230,000 series, and that's quite expensive. If you want to look at the actual numbers, if we're trying to grab a month's worth of data at 1 minute resolution, to even hold all of those 230,000 series in memory, it's going to cost you about 147 gigs of memory, and then you have to perform your aggregation functions on top. So to do that, it's going to take about 10 billion computations. So it's actually extremely expensive to sort of return all of this data, which is why you generally get an error, and a lot of the vendors or your metric systems don't let you query that much data. Now, there's an easy workaround for this, which is to pre-aggregate this stuff, right? So the manual workaround we used to tell our users before was still omit the really high cardinality stuff, because you're not abusing it and using the system the wrong way, and this gives you a great breakdown into the details of your data. But in addition to omitting that, also omit a second metric where you don't have as many tags, right? So omit a second metric where you only have one tag on it called the endpoint tag, and that's only going to produce 10 time series, and it's going to unblock your problem. Now, as a little caveat here, you generally need to change the name of the metric so that you don't pollute the old namespace, right? And that's a little bit annoying. And also, if you want a different rollup view, so if you want to look at all of your latencies by version, you have to yet again go and emit another metric. And if you want the endpoint and the version, you have to yet again emit a third metric with that particular combination and come up with a different name. So this is quite a tedious task, and a lot of your service code ends up becoming just monitoring code, which sort of sucks. Not only that, every time you want to create one of these aggregates, you have to redeploy your code again, right? So you've lost visibility into your application. You have to go and implement one of these pre-aggregates and then roll your service back out again before you get visibility back. So that's quite annoying. And finally, on top of all of that, each one of these aggregates produces even more time series that you have to store, right? So it's not quite as many because there's less tags here. It's not quite as many as the original 230,000, but it's still more time series that we have to store nonetheless. So this leads us to our second problem, which is the storage costs of storing, 230. Well, when we add the aggregates on, we're at about 250,000 series for this particular example. Now, 250,000 series may not seem like such a large number to store, but you've got to remember this was for one microservice, right? So if you're running at a scale like Uber was, and you have 4,000 microservices, this quickly adds up to like 1 billion time series that you have to store now. You might not think this is a relatable problem. You might think, I'm never going to have 4,000 services. You also have to remember this was just the latency metric. So for your particular service, you might emit other metrics like error rates, success rates, request counts, etc. And if you just had 20 metrics per service and 200 services, you get to 1 billion time series anyway, right? And 1 billion time series is extremely, it's a pretty large number of time series to store. So going back to the beginning, we had already written our own custom time series database in 3DB, and that gave us a great sort of, it had great efficiency. So it gave us a compression ratio of about 11x, which was great. Now, we couldn't really crank out another order of magnitude of improvement on top of that, because for us to do that, it would mean, so for us to get another 10x efficiency on top of that, it would mean that we would have to only use a single bit to represent a metric data point, which is actually impossible. So we weren't able to create a sort of orders of magnitude of any more efficiency in our storage tier, right? And there wasn't really anything we could do to sort of make the storage of all of these time series more efficient. So instead of doing that, we sort of dug into an individual time series, and we looked at the lifecycle of an individual time series through our system. And this is pretty similar to how a lot of the other open source systems work and a lot of the vendors work. A raw value will come into your time series database, and you have some sort of like asynchronous consolidation or downsampling process, right, where you read the high resolution metrics and you write it back in low resolution, and you end up with something like this, where you only keep the high resolution metrics for a certain period of time. After that period of time, they get downsampled, stored for longer at a lower resolution, et cetera, right? And we do this for two reasons. One, efficiency. It's much cheaper for us to store a year's worth of data at 1 hour resolution than at 10-second resolution, for sure. And the second reason we do this, and we can get away with it, is when you look back like for a year's worth of data, you can't actually, there's only so many pixels on a monitor, right? You can't actually see 10-second granular details when you look back that far. So we can just return you the 1 hour details. And as long as we sort of preserve the accuracy of the data, and to do that, we really have to store a statistic, right? So every time we sort of downsample 6 10-second data points to a 1-minute data point, we can't just average and store one data point. We actually need to store the statistics of it, which includes like the min, the max, and things like that. And the reason why we have to do that is, when you have a query function that's looking for the min, if we give you back the average, it's no longer a statistically correct answer anymore. We have to return you the min, right? Cool. So if you look at this retention resolution pattern here, in the same way that for really high detailed data, so for really high resolution data, which is 10 seconds, we only saw that for 2 days for efficiency reasons. We can really apply that to high cardinality as well, right? So if you go back to our example where we have the high cardinality metrics, and you think about the use case of why you would want all of these metrics associated with it, you have the host name there, and that's probably used when there's an issue and you want to drill down and respond to an incident and find a root cause, right? Do you really need to store the metric with the host name associated with it for a whole year, like we were for all of our metrics? Probably not. The chances of your service running on that host, and this is if it was a physical host, these days it could be running a container or even a Kubernetes pod, and the lifetime of those things are maybe just a few hours. So the usefulness of storing this metric for a whole year is not that high, right? And we can actually get pretty good storage efficiencies if we just didn't store it for a whole year, if we only stored it for 3 days, right? And 3 days can give you enough time in case, you run into an issue that's not super urgent on a Friday afternoon and you want to deal with it Monday morning, you can store it there for 3 days and sort of still dig into the data. So this sort of, if we just store this high cardinality information for 3 days instead of a whole year, it gives us about a 10x storage efficiency gain, which is pretty nice. You may be doing some maths in your head right now thinking, hey, 365 divided by 3 is 120. Why am I not getting 120x storage saving? We're still applying the same resolution and retention policy. So for those 3 days, we're still storing 2 of those 3 days at a 10-second resolution, so you get the details. And then for the third day, we store it at a 1-minute resolution. So really, the cost savings are really for the other 363 days, which is mostly at 1 minute and 1 hour, but still a 10x saving, which is an order of magnitude, which is pretty nice. So now if you look at the aggregate view above the host tag, so if we look at it without the host tag and you've aggregated it with just the version, you think about the use case again here, right? Why am I emitting these metrics with a version tag? I'm trying to compare how my new version is doing compared to my old version so I can roll back a deploy or something like that. And potentially keeping this data around for a few days just in case you want to catch edge cases that don't occur or some sort of slow degradations. If we stored this data for about 2 weeks, you really get all the usefulness out of it, right? There's not really a need to store it for a whole year because the chances of you looking at what the version was a year ago and comparing it to the current version is fairly low. And if we stored it for like 2 weeks or 15 days instead of the whole year, again, we get a pretty good storage efficiency saving. Now, of course, there's going to be certain metrics that you do want to store for the whole year, and they're useful. And if we look at the one aggregate view above this again, without the version tag, now we have the status code, the name of the endpoint, and the client that the requests are coming in from, right? These are things that don't really change over time. And because they don't change over time, this is the sort of information that you do want to keep for the whole year, right? But because this is no longer really high cardinality because you've dropped the other 2 tags, there's only really 5,000 series, storing them for the whole year and using it for things like anomaly detection and capacity planning is fine because it doesn't actually take up that much storage, right? Cool. So the 2 problems we're trying to optimize for is both the query performance so that we can return you an aggregate view of all of your rollup data without having you to go back and implement a lot of pre-aggregate code and having you to deploy your service again and again. And at the same time, we're also trying to store both the high cardinality metrics because they were really useful in the case of an incident, and all the aggregates in an efficient way. And we wanted to do that by providing flexibility on the retention of this data. So we looked around for some solutions and saw how other systems were solving this. And the one common pattern that we saw again and again was this concept of this sort of asynchronous evaluation process, right? This sort of worked in the same way that our consolidator did earlier when we were trying to downsample the data, but it did a little bit more than that. So it would also sort of downsample data by reading high resolution metrics, downsampling them, and writing them back into the time series database. But they would also sort of do this aggregate for you as well. So they'll read the high cardinality metrics, perform the aggregates asynchronously, and then store them back into the time series database again. And on top of all of that, it did it in a dynamic fashion, which was pretty nice. So the most popular example of this type of design is probably Prometheus recording rules that you may know of. And we're going to go through this example here just because it's the most well-known, but Influx has the same thing. It's called continuous queries. I think Cortex is the same thing. It's called like a ruler component or something like that. And the way these things work is you have an expression, which is essentially your like a query that you want to execute. And it will execute the query against the data, and you get the results, and you store the results back into your time series database with a new ID, essentially, which is what is in that record line there. And this is nice because you can do things dynamically, right? So you can emit, you just have to have that single line of code that emits your high cardinality metrics, and you can come along later on and create one of these aggregate rules. You don't have to deploy your service code, which is really nice. The second thing that this is good at, and this really helps our efficiency, is that if you look at the expression, there's a particular aggregation function that we're applying, right? And this is the thing that I've highlighted in red here. It's the sum function. So we already know when you're aggregating this data, like how you want to aggregate this data ahead of time. So we no longer need to store all the statistics for this use case, right? For this aggregate, we know you want to have it summed up all the time. So we don't need to store the min, the max, and things like that. So we're storing less data per data point, which is nice. And the final thing that's good about this is you also sort of can define your resolution at the same time that you're defining your aggregate. So if you look at the thing I've highlighted in yellow there, you're really saying aggregate this data and drop the host tag during my aggregate, but aggregate this data at a 1 minute sort of resolution, right? So you can define both of those in one single feature or mechanism, which is good. There's a couple of things that this doesn't do, unfortunately. One thing that it's not good at is just straight downsampling. And the reason why this is not good at downsampling is because the way this works is you read the data and you can apply a particular rate to it, like 1 minute and 1 hour. But when you write it back to the time series database, you have to give it another ID, right? And this is going to be tricky because now you have your sort of metrics stored at different resolutions with different IDs. So if you're looking back 2 days, you need to know to look for latency. If you're looking back beyond 2 days, you need to change the ID of the metric that you're looking for. So it's not really a mechanism that you could use for downsampling, so you have to have a separate mechanism for that. And the other thing that's sort of missing here is retention. There is no any concept of retention here at all, right? So while you can define your resolution for your aggregates, you need another mechanism that's going to sort of apply various retention to your data for you. In addition to all of that, it's sort of had the same shortcomings that we found with our consolidator. So we ran into a whole bunch of sort of issues when we were running our consolidator and having that perform the downsampling for us. And the first issue that we ran into is that it actually put a lot of load on our time series database. So if you think about it, your time series database is the thing that's taking all of your writes and serving all of your reads. And on top of that, you're now also reading every data point that's written multiple times to downsample it. And then for every aggregate you have in your system, you're also reading the data again, aggregating that and running that back into time series database. So for every one data point that's coming into your time series database, it's getting written and read to and from persisted disk multiple times. So it took like a decent amount of load out of the time series database. The second sort of complexity that a system or design like this needs is you sort of need persisted state of like where you're up to, right? Because this evaluator can sort of go down at any point in time, and when it comes back up, it needs to know what have I downsampled so far, what have I aggregated so far, and what do I continue need to do, right? And that you need some sort of persistent state there, which means you need another storage component to your metrics platform. So just added to the complexity there. And finally, you needed like a watcher component. So something that's like looking over the evaluator and ensuring that it can get through its work. And the reason why that's so complex is the amount of work it has to do is highly variable. It depends on the number of time series that's coming in because you have to downsample all those time series. And it also depends on how many of these aggregation rules you have, right? So the more rules you have, the more work it has to do. And because it's asynchronous, something needs to keep watching and making sure that that evaluator can get through all the work in the limited amount of time that it has. Because if you think about it, if you're taking raw values and you're only keeping them for 6 hours, you need to create all of your downsamples within that 6 hours, because otherwise the data is gone for good, and you're not going to be able to create the downsampled values. So this all made the system fairly complex. So then we thought of a different design where we thought, hey, what if we had a central aggregation tier where you can write all of your raw values, and this aggregation tier will generate both your high resolution metrics, your low resolution metrics, so it will do the downsampling for you, and it will also emit all of your high cardinality metrics and do the aggregations and emit your low cardinality metrics straight into your time series database so that you don't have to read and write from the database. So what this looks like, sort of closer up, is we're going through the same example, so it's the latency metric with all the tags that we have, comes into an agent/proxy thing that we call the coordinator. And the coordinator is responsible for applying policies or rules onto the metric that is coming in, right? So the first type of policy that it applies is essentially we call it a mapping policy, but essentially it's a downsampling policy, right? So what you're saying is that, store these metrics, and we have a filter, so, apply this rule for all of my latency metrics, but you can imagine you can change the filter for any subset or any individual time series. But for everything that matches this filter, I want to have it stored and downsampled, and stored for 2 days at a 10-second resolution and 15 days at a 1-minute resolution. And what the coordinator will do is take the incoming metric and write it to 2 separate entries in our aggregation tier, right? The first entry actually aggregates things at 10-second resolution, and the second one aggregates a 1-minute resolution. And at the end of those respective periods, they will independently flush to the time series database, right? So we no longer have to read the data and write it back in. Similarly, we can also do this for aggregates. So we have a segment type of policy, and this type of policy is called a roll-up policy, where we perform our aggregates. So it looks similar to the mapping policy. You have a filter, so you can apply it to a subset of your metrics, and it's fairly dynamic. You also have a bunch of tags that you can roll up by. So in this example, we want to roll up everything by the version tag. You can specify the aggregate function that you want, just like we did in the Prometheus recording rule, which is sum. And finally, you can also specify the policy. So for these aggregate metrics, I want to store them for 40 days at a 1-minute resolution and a year at a 1-hour resolution. So the coordinator will take that same data point that's coming in and also write it to 2 more entries if you have an aggregate rollup rule. And the first entry is the aggregate time series at a 1-minute resolution. The second one is at a 1-hour resolution. And again, those independently after a minute and after an hour flush to the time series database, right? So this design has the same advantages as the asynchronous rule evaluation because we're doing things dynamically here. You can emit all of your high cardinality metrics into the coordinator, and you're applying the rules dynamically. You don't need to redeploy your code, which is nice. You're also able to do the aggregates here and define their resolution at the same time, which is pretty nice. And you're also defining the aggregate function. So again, we don't need to store the whole statistic anymore. So that's an efficiency gain. So it has those advantages, and it has more, right? We can now do the downsampling here with the same mechanism, right? It's going to store your original metric under the same ID in order to store it for the different resolutions. So you can use, get a downsampling in the same function, which is pretty nice. And the other advantage of this is we are also defining the retention now as we're defining the resolution, right? And so you can have them defined in the same place. And the aggregation tier doesn't necessarily do anything with the retention. It really only cares about the resolution and the aggregation function. But how it uses the retention is that at the end, when it's flushing to the time series database, depending on the retention, it would route it to the correct either cluster or namespace that you set up in your time series database. So you only have one set of definitions, and you can define your retention and your resolution in the same place, which is pretty nice. So you don't need another mechanism for that. On top of all of that, it's a synchronous system because you're doing all the aggregation on the way in, right? So you don't need to store persistent state of where your aggregation is up to because it's no longer an asynchronous system. You don't need a watcher or anything like that to make sure this is keeping up with the workload that it has to do because it knows all the workload sort of up front. Cool, so zooming out a little bit to talk about how these consolidators work. The consolidators can be run as a daemon on a host if you have physical hosts. It can be run as a daemon set if you're running Kubernetes on Kubernetes node. It can even run as a sidecar if you're running Prometheus. And what the coordinators do is read the rules from a central store, right? So you can upload these rules to a central store, and we use etc.d as our store. So you can upload all of your mapping and your rollup rules, and all of the coordinators will be reading the rules all the time to apply to the metrics. This is pretty nice because it sort of takes the complexity of applying the policy to the metric and pushes that down to the coordinator much closer to your client and doesn't have to do it in the aggregation tier. So the aggregation tier is fairly simple in that way in the sense that it only has to perform the aggregation. Another nice property about doing the policy matching on the client is you're pushing a lot of the resources down to the user of the system, right? Like you're pushing it onto their hardware now, which is nice. And another good property is, if you think about it, each coordinator is not going to see every metric for your system. It's only going to see a subset of metrics, the ones that are produced by the clients on that particular host. So it doesn't have to apply all of the rules, which is nice, just a subset of them. And because you have the same clients pushing to the same coordinators, you can essentially cache a lot of the policy hits, right? So it sort of ends up being your rules from the central store is sort of distributed, is sort of cached in a distributed fashion in all of your coordinators. So that works out pretty nicely. Now, we wanted this aggregation tier to be scalable. So we just took all the entries and put them into shards. And now when you add a new node to the aggregation tier, it just takes over an existing shard from an existing node. So it's pretty scalable that way. We also wanted it to be reliable, so we added a replication to the shards, right? And the way this works is, if we look at one level higher than this, you can have an aggregation tier that has multiple replicas, and you can spread those replicas across multiple zones or multiple regions. And the way this works is for a particular replica set, they'll sit in one particular zone. So if you have like a zonal outage, you're still good. And between the replicas for a particular shard, so for shard 1, there's a replica in each zone. They actually do a leader election amongst themselves. And there'll be a leader and a follower. And they both perform the same aggregations, but only the leader flushes to the time series database. They both need to perform the same aggregation because if the leader dies mid-aggregation window, it's lost all of its progress for that one aggregation window, right? So you need the follower to also have all of the progress for that aggregation window, and it just detects that the leader has died, and it will sort of take over and flush to your time series database, which is nice. Another advantage of spreading this across multiple regions is you can have global aggregates now, which is pretty sweet. Cool. So this design also gives another advantage, which is that it adds even more flexibility in the sense that not everything now has to go through the aggregation tier and be persisted to your long-term time series database. You can even, because you have this proxy tier now that's applying rules, you can even push some of the metrics to like a local time series database instead, right? So you can imagine you can run like a Prometheus on the node, or you can run like a single M3DB node there. And what a nice use case of this might be is your system metrics, right? So all of your CPU, memory, disk usage, things like you probably still want those types of metrics downsampled in your long-term replicated store, but at a high resolution, it's nice to store them just on the host. And when you need to do alerting to detect when there's too much CPU usage or your disk is running low, the alert can go straight to the local time series database, right? So it's really pushing a lot of the costs down back to the client. Now you may think this model is pretty similar to Prometheus, but it's not, in the sense that it's not like all of your metrics go to the local store first and then you selectively pick which ones go to your long-term storage. You're actually selecting which ones you want in each of them, right? Cool. So to summarize a little bit, we sort of solved the two problems that we sort of set out to solve. You can now have great query performance because you can dynamically create all of the aggregates for your high cardinality data. And you can do that without having to deploy your code, which is nice. And at the same time, we've managed to sort of efficiently store these things by giving you a flexible retention and resolution control, which is nice as well. So those are the two problems we set out to solve, and we have done so. If you're using a vendor right now and your bills are particularly high, you should probably think about the same sort of feature set that we're sort of trying to push here which is, do you really need all of your data to be stored for 15 months or a year? Is that really, are you paying for storage costs for stuff that you don't really need to be paying for? And if so, maybe you should push on your vendor to provide flexibility like this, right? So you can store the high cardinality data for a much shorter period of time and only store the data that you really need for the full year, and also, if you are running a metrics platform yourself, this is all open source, so feel free to just sort of run ours as well. Cool. That's really all I had.